Okay, I've been doing some experimentation here, and I find something rather weird. If I have just two convolution layers right here, everything works just fine. If I had to focus, even if I use only the momentum update, which is not as good as Atom, but just the momentum update, everything works just about. It works very quickly. But as soon as I add a third one, I mean a third set of convolution layers, everything stops working. At first, I thought that I had made a mistake again, but the cause of the error is read the size of each convolution window. Like here, I'm translating from weight, which is almost 200, 170 something, all the way down to 64, all the way down to 32, and shrinking things this quickly it really causes the gradients to get compressed. Like let me run it right here. I have a visualization. Okay, as you can see right here, these are the gradients, the outputs, the weights, the deltas. The outputs, the weights, the deltas of each image. Right now, everything's getting focused because of the focus layers. Everything's fine, but as soon as I shrink it, the focus layer is no longer enough. I mean, the focus layer does something, but it doesn't do enough to really overcome the problem of well, the window is just too small. It's just getting too small, and everything's getting compressed, which causes the auto weights to get all the deltas to get compressed, and the sum just gets too high. As in right here, when you're doing the convolution, we're taking we're doing the convolution and we're summing everything up, but eventually the sum gets way too high. Uh, there are several solutions to this. One is instead of taking the sum, we take the average. This is what we do when we're doing image convolution. As in right here, when we're doing the convolution, we just take a counter and then we take the average of the sum. But that works for image. In image, it's basically necessary to do it that way. But in here, in neural networks, that just doesn't work because the average is not the same as the sum. It's nowhere close to it. For an image, it works fine, but for a neural network, we have to do backpropagation, and the learning will just get messed up if we try doing that. The next solution, there are several, is weight initialization. There's something called Xavier initializations, and basically you set the weights to limited values that make everything work better. I don't actually like that, but I'm going to show it anyway. But I'm going to code it anyway. But know that it's something I really don't like doing because it works differently depending on your hyperparameters. For example, if you use SIGMOID or RELU, it works one way. But if you use hypertangent, then everything's different. That's why I don't like messing up with hyperparameters. I like my networks to just learn the same thing no matter what hyperparameters I use. So I'm just gonna code the weight initialization anyway, just to show it, but I really don't like it. Okay, step 1, fill random. Okay, I'm gonna rename fill random to fill random uniform because there's gonna be different kind of randoms here. Fill random uniform. That's step 1. Fill random uniform, kernel random uniform, and we're done here. Okay, next. We need a fill random, what's it called again? Fill random normal. Fill random normal. Okay, we'll just copy and paste. Change the name. And make sure we put everything in the right place. Otherwise we get an error. Fill random normal. I'm not gonna specify mean and standard deviation. That would just take too long. Okay, what do I call it? CUDA random normal. CUN normal. CUDA takes care of calculating the normals anyway, so we don't have to worry about that. Okay, this part is done. That's the second part. We don't have to do much work here. Now comes the third part. field random. There are different names for it. It's called Xavier initialization and something like HE initialization, but I'm just gonna call it Xavier. Okay, Xavier initialization, also called Glorot initialization. Yeah, well, that name doesn't really sound any better than Xavier, so I'm just gonna call it Xavier. Xavier or Xavier or Xavier, whatever. Okay, let me just rename everything first. Just make sure everything fits just the way it's supposed to. Okay, now let's try to code exactly how it works here. I gotta remember how this works. Okay, result equals. Oh, we still do the normal, but we have to multiply the normal by something else. Okay, unsigned type neural unit, CUDA neural unit. Okay, we need a value. Okay, I'm looking up the equation here. It's glotalization is alpha squared 1 divided by fan in. Oh, or fan in times fan out divided by 2. There are several versions, but I'm just gonna do them all. Like I said, I really don't like this one because it works differently depending on what system you're using. Okay, step 1, we need to calculate the equivalent value. Just taking this one right here wouldn't work right here. So let's just copy this. Okay, Q1 value. Okay, what the? Oh no. Value thing here. Okay, value equals this. Now that we have the value, we need to modify it, and we need some parameters here. Okay, length. We need the fan in value and the fan out value. Whoa, that's really complicated. Okay, unsigned long seed. Okay, we need source length, and because the way it works is that we have an input layer, and an output layer. So we calculate the average length of between the input and the output, and we divide the whole thing by 2. We take the average of the two, and that gives us the value. Then we take 1 minus the average to get the mean. I think I don't remember how it works. To get the mean. Well, anyway, what it does is that it just reduce the value to some acceptable range. That's what it's supposed to do. But like I said, it really doesn't work the way it's supposed to. It's never works for me. Okay, next thing. Let me just code it and we'll see what it gives later. Value times. Oh, do I have source length? We're just renaming everything. Source length, result length. Okay, result length. Okay. Result length. Okay, I have to make sure I got everything right here. Yeah, CUDA animal state. Result times. There are 3 different versions. First of all, let's do Xavier initialization, just so I don't forget which one I'm using. I'm looking at the equation, trying to figure out how to code it. It's the value. Okay, times 1 divide, no, 1.0, 1.0 as, oh, wait, what am I doing? 1.0 divided by SQR square root, no, SQRT square root of source length. Okay, let me just get the equation right here. I think we need to find the fine average first. Okay, get the fine average. Get the average. AVG, average. Okay, average equals source length plus result length. No, result. Yeah, result length divided by 2. Okay, let's just put it in parentheses just so we don't forget. Source length divided by 2. That gives us the fan average. Okay, that gives us a fan average. So result equals value. I'm getting multiple interpretation. They are all contradicting each other. Let me just find a good one. Okay, 1 minus square root of average. Okay, there are multiple sources here. They all say something different, but I'm just trying to figure out which one is correct or if any of them are exactly correct. Xavier initialization. Okay, so it's 1 minus the average of the source and the result. So that's the Xavier initialization. One divided by the value times 1 divided by the square root. You don't need to put it in this, but let me just double, just to make sure that we get a good value here, because sometimes C tends to be really picky about everything. Okay, there's also another version. Result equals, I'm just gonna show all of them. Result equals value times 2 divided by the square root of the source. Of the source. This one's called HE initialization. I don't know why it's called that, but that's why it's called. I have no idea. Okay, these work sometimes, but not all the time. There's a third one. Result equals 1.0 divided by square root of the source length. No, not square root. This one doesn't require square root. 2 divided by the source length. Okay, 2 divided double source length. Source length by itself. Okay, this one's called LeCun initializations. LeCun initializations used for CELU. Okay, I'm just gonna try the Xavier one. But I'm not done coding yet. Okay, results Xavier. Okay, launch source length. Okay, we need to specify the source length and the result length. This is not the length of the array itself. This is just, we have to separate them just so the system doesn't get confused. Okay. This shouldn't be necessary, but just for safety, I see a possibility that the source length and result length might get confused here. Because it's not really clear which one it means what. But anyway, source length. Okay. Have to make sure you get this right, otherwise we risk having a problem. Okay, source length, result length. Okay. That should be do for now. Okay, so let's go back into the library and make everything do what it's supposed to. Nope. Okay. Fill random uniform. Okay, let's copy everything. Fill random uniform, fill random normal, and fill random Xavier. And make sure you got everything in the right order here. Get it back. Okay. Is it in the right order? Yep. Okay, we didn't specify source length and whoa, fill in them normal. So oh, long. My mistake. My mistake. Mistyped. Okay, it's all right. Yep. Uniform, not uniform. Uniform. Is it good? Yep. Okay, build. Okay, it's built successfully. Now let's modify everything back here. Okay, there are two places we need to modify. Convolution and bias. Actually, convolution doesn't, bias doesn't require anything. It's only in convolution so far. Field random, uniform, field random Xavier. Okay, not Xavier, Xavier, X Xavier. Okay, parent layer weights. Whoa, we have a problem. Oh, that's a problem. That's a problem. It's obvious, but I missed it anyway. The length of the array is not the length of the layer, it's the length of the outputs and the length of the deltas. The actual array has nothing to do with anything. So let's go back here and fix that. Unsigned long, source length, result length. Okay, source length, result length. So I call it source length or fan in. Oh, but anyway, it doesn't matter. Oh, the names are just change the names to fan in. Fan in, fan out. I'm confusing myself here. Fan in, fan out. Just make sure the names are not too confusing. It was so obvious and I missed it anyway. Okay, let's change the name here. Fan in, fan out. And length. Seed, fan in, fan out, and length. Get rid of that. For I equal length. Fan in plus fan out. Fan in or fan in. The 1 divided by square root of the average. Is that it? Yeah, that should do it. Okay. Now let's rebuild again. See if that does it. Oh no, it didn't work. I missed something. And of course, I forgot to pass the parameters into it. Oh, that's just stupid. Okay, let's rebuild again. Okay, so now let's figure out how to call the function, the Xavier function. Okay, it's definitely parent.layer outputs. Layer outputs. Oh wait, no, it's not layer outputs. Oh, I forgot that I specify. I'm inside creation. It's layer length, source width. Okay, source depth. Oh wait, I need to calculate the full length of the source array because it's not as simple as this right here. Okay, now I need to compute the calculations of source width times source height times source depth. Oh, that's just gonna be tedious. Like I said, I just really don't like this. Times source height times source depth. That's fan in. And now for fan out. I'm not gonna bother just trying to make this look good because I really don't like it. result width times result height times result depth. Okay, that gives us the full length of what we need, I think. It's still complaining about something, but I'm pretty sure that's right. Oh, wait. I think I forgot to modify something. Okay, now it's built. Let's see what happens. Okay, first problem. It works, but if you'll notice the numbers here are very, very, very small. Like it starts out very, very dark. And this is the reason why I don't like this. Because it solves the exploding gradient problem, but now you got a vanishing gradient problem. You can't really get everything right perfectly in the middle because it's very arbitrary. Like it picks a value that's supposed to be right, but it's not right for every situation. It completely depends on the architecture of your network. Like yeah, if the network is designed one way, it works. If your network is designed another way, it doesn't work at all. As you can see right here, it's learning, but not very quickly. I mean, it will solve the basic problem of the network being broken, but at the cost that it just doesn't learn at all. I mean, some other version might work, but I'm gonna try them all in turn. But as a rule, I really don't like this. The the basic idea of it just doesn't work. I'm gonna try the other ones. Okay, just to correct something here. This right here, the H-year initialization, it uses the square root just like this one. The square root of double fan-in, and they all use square root. It's the square. Okay, let me just rebuild it and try again. Okay, and we're back here. Same thing again. Everything starts out really dark and the weights start out very, very small. Like with 0.0.0.0 something. This is, I mean, if you let it sit right here, eventually it will work. But again, I really don't like it. It solves one problem by creating a completely opposite problem. And even if it does work, it completely depends on the architecture of your network. That's why I don't like it. So let me try the third solution. I'm not going to try the other type of initialization right here because it does basically the same thing, just in a different situation. So let me try the third solution, which is just clip the weights. Well, you can't clip them exactly, but it does the same thing as the focus layer, but it does it better. In my opinion, it does it better. Okay, let me look at it again. Yep, it will work eventually, I think. But the weights are minuscule right here. Maybe it works depending on your hyperparameters, but I don't like it. So let me try third solution right now. Okay, third solution. What was it? Okay, where am I? Yep. Let me just get rid of this. I don't like it. Fill random. Fill random uniform. Uniform. Okay. Now, what am I doing? Fill random uniform weights. Get everything back there. I'm just gonna keep the code right here, but if you want to use it, fine, but I don't like it myself. Okay. Where's the other one? Okay, let me go back somewhere. Convolution, reverse convolution, forward. Okay, what I'm going to do is right here, it takes the sum of all the weights. If the sum is outside a certain range, I mean, we have the focus layer, which puts the weights when they're above 1, it pushes them in the center. However, it doesn't work if the weights are too far from 1, like if they're 10 or 20 or something. Okay, before we do that, let me show exactly what happens. Okay, let me take away everything here, show you exactly why everything doesn't work. Okay, let's run it and compile. Yeah, yes, compile. Okay, let's just see everything. Okay, first thing, we get not a number, infinity. Basically, the gradients explode so much that everything just gets messed up completely. So far we're using what we're using. We're using the standard momentum, but even with Atom Optimizer, it's still messed up a bit. Let me show you. This shows us exactly what is happening here. Here we have the deltas are 13 something, 24 something, which is way too high. Even with the focus layer, that's too much for it to handle. And here it's that negative 788. That's also way too much. And here the output's at 10 something, 18 something, 18 something, and now you have 2000 something. The activation function is preventing it from the output from going too high, but it's doing nothing for the backpropagation part. That's why you have 64 here, 206. The numbers are just exploding. The Xavier function causes everything to shrink close to 0, which is good, but not good enough to really work. And without the Xavier function, everything just explodes. So we need a way to fix this that doesn't shrink our weights to something that doesn't work. So we're going to do a very, very janky solution. I mean, it works, but it looks ugly, but it gets the job done without breaking anything. That's the important part. Okay, first thing. For each pixel, it gets the sum across every single pixel in the convolution. And we're just going to take the sum right here. Let me just get rid of this here. Okay, if sum is less than, we need to pick a number that's more than 1, because at 1, because the weights have to be allowed to go out of bounds. Because the way the learning works, if you clip it too close, then the learning is not going to work right. So we pick a number right here. 5 may be too much. Let's say 3. 3 should do. It cannot be 1, but it has to be able to get way above 1, but not too far above 1. Or sum is more than 3. No, less than -1. Less than -1, or no, less than -3 or more than 3. So we can adjust the number right here. For example, if we're doing fully connected layers, the 3 wouldn't be enough, because sometimes the numbers get way high, as much as 10. So for convolution, 3 will do. 1 is too small, 2 maybe, but 3 is within range. The focus layer should take care of everything else. Okay, now we have to go to every single one of oh, wait a minute. Oh, wait a minute. Filter index. Oh, I thought I made a mistake, but it's fine. Okay. Now we need to copy everything down here and then do it again. Okay. We need to go back to over every pixel in the weights, every filter, and then divide them, multiply them by 0.9. The point is if they get too high, or no, too far out of bounds, too high or too low in the negative, we have to shrink them. Same thing as the focus layer, but for much bigger numbers. With the focus layer, we have to be precise to try not to overwhelm the system. But here we don't care about overwhelming the system, because we're far out of what is acceptable. So we have to go back to the index, and then do a loop to every single pixel. Okay, for j equals 0, j less than for I equals 0, I less than source count. Oh, and also, if sum is out of bounds, set sum to 0. Because if it's out of bounds, we shouldn't be backpropagating a number that's way too high, because that's going to mess up the learning. Just set it to 0. Okay, now we didn't take every pixel in the filter and set it to an acceptable value. So source count. How do I go to all the pixel? I need to know where I am exactly. Okay, for filter index equals which filter are we operating in. For I equals source count, we need to go to all the filters. Okay, now we need for j. For each pixel in the filter. Not tab. Tab. For each pixel in the filter, j. We're not using the j anymore, so it doesn't really matter. For j equals what? Filter length. Yeah, filter length. I think it's filter length. Yeah, for each pixel in the filter. We multiply that filter dot filter index plus j for each pixel in the filter. For each pixel in the filter, we set it to what exactly? We multiply it by multiply equals by 0.9. Basically, it tells it to shrink. This is not the same as the focus layer because why is this? Oh, it's still running, and it doesn't work. It's running, but it doesn't work. I kept it running just to see if it will work, but it doesn't. And the more layers we add, the worse it will get. So that's why we need this right here. Okay, so you multiply every pixel in the filter by 0.9 so that the result will be within the range from 0.3. Once we reach between 3 and -3, the focus layer and the network learning itself will take care of the rest. After that, we don't need to worry about it. Okay, now we have to do it the same way it does right here. Filter index plus equal filter length. Okay, that's it right here. I'm trying to reproduce all the code here. I don't have to think about this again. It's just too complicated. Okay, I'm trying to reproduce everything here. If sum equals 0 because we don't want to backpropagate any value that's too high. We take the address of the first filter that we're doing with, which is in the row, and for each of the filters, for each pixel in all the filters, we multiply it by 0.9, and we move and when we advance to the next filter, and that's it. Okay, now let's compile it, see if it works. And it works slightly better. I think I'm still using whoa, it works extremely well. Okay, the weights are small, but not too small. I'm still using the normal, what do you call it again? No. It stopped. Okay. Wow, it works extremely well. That's really weird. Normally everything fails. I'm used to everything failing, so it's really surprising. I'm using the momentum update, which is not the best one. So that's why it's taking a little longer than usual. But if I was using Adam, it would work a lot faster. But so far, the weights is 0.05. The error is. So it works extremely well. But like I said, it's just a very, very weird solution to a problem. Okay, it's right here. Okay, what were you doing here? If it's out of range, we take for each pixel. We take for each filter, for each pixel in this filter, multiply the 0.9. Just shrink it down. Maybe we should make it 0.99, but 0.9 it's fine. So we don't need to go too far. Okay, so I think that solves the problem. Let me just try Adam, and just to make sure that it works with that too. Okay, here it is with Adam. The Adam optimizer works extremely well. Like, really, really, really well. Like immediately you get better results. We go from 0.05 to 0.01 right away. Okay, while I'm still here, let me make a few other changes. There's something that has been bothering me since the beginning. In the momentum thing, I've been wondering if I should learning rate times deltas or learning rate times vectors. But I think learning rate times vectors is better because the deltas, they're supposed to be the derivative for the weights, and if you multiply it by the learning rate, you're just messing things up. Like if you multiply the learning rate by the vector, we're just moving more slowly, but we're certain that we're moving in the right direction. So I think they work better. So same thing down here. It's gradient times vector. The adaptive gradient times vector. Adam still does does everything like that. So maybe that's why it was working so well. I still have it right here. Yep, it's still running and it's still running perfectly. Before we leave, let's just try something else. Oh, and something else that's been bothering me right here. I don't have to pick between them with a function call, and I've been avoiding this, but let me just do it now. Unsigned long, optimizer, switch optimizer. Switch optimizer. Case. Type neural network. Okay, let me just define this right here. Let me just do this offline. And we're back. I've been coding a few things. Nothing really big, just some cosmetic quality of life stuff. Okay, first of all, I put in the optimizer in their own separate switch function, like here. Instead of having to manually recode everything, I just need to recode everything right here. I just have optimizer, momentum, and set it to default values. We can change them right here instead of having to change them in the code. Like I said, it is nothing really different. It's just quality of life stuff. It just makes everything look better. Do that in bias, same thing in bias, and same thing in. Whoa! Oh, no. I thought I missed something. Oh no, I didn't. It just looks weird, but it works. I have a few minutes, so let me just try something else. I don't know what I'm going to do. I'm just going to waste a few minutes. One little thing that I've been meaning to code. There's lots of little functions I've been meaning to code, but they don't actually fit anywhere. They're just there's stuff I've seen in NumPy and TensorFlow when reading the documentation. They have lots of little functions that do random little stuff. So let me just do one of them right here. Okay, since I'm filling stuff, let's just do fill one hot. Sometimes you need to fill a one hot vector. So this is it right here. Let me do it real quick. So I do fill one hot. Fill one hot. Like a one hot vector. Okay, we need an index and length. Okay, let me just do that real quick. What's the index? 4. We don't need any of this. Any of this. None of that. We need an I. Okay, for I equal length. If I equals index, result I equals 1. Else result I equal 0. And that's it. Well, that was an easy one. Fill, no, not random one hot, just one hot. Fill one hot. Okay, here, instead of fill random Xavier, well, actually it's the same thing. Fill one hot. We don't have to do anything. Just fill one hot. Fill one hot index. Well, that's a really easy one. Normally they're harder than this, but it's nice to see something that doesn't really break me. Index. And I think that's it. Yep. Index, array length, fill one hot. Just go to every single one. The one that corresponds to index at 1, everything else gets 0. And that's it. Something that's actually easy. I feel like doing something else, but we don't have time. Oh wait, we need to add it in the list. To our going list of functions. There's gonna be many more to come, but this one's done at least. Eventually, you're gonna have to do dropout and other stuff like that. And wait, we gotta build. No, you have to turn off the program first. Oh, it's been running. And we build. Just make sure it works. We didn't miss anything. We didn't miss anything. Come on, come on. It's taking a long time. Okay, and it works. So everything's done. So we're good now. So see you later.